Hello, everyone. Welcome to the 41st meeting of New Directions in Group Theory and Triangulated Categories. Today, our speaker is Jesper Grodal from the University of Copenhagen, and he'll be speaking to us about, well, the title of his talk is A Guided Tour to the Picard group of the Stable Module category.
Thank you. So it's a great pleasure to be here, and it's a great pleasure to see so many friendly faces in the audience, and also so many experts. So with this talk, I thought I would give sort of a sort of gentle introduction to what is known currently about the Picard group of the stable module category, and this is a topic which has a long history. And this Picard group of the stable module category, I can already reveal now, is also sometimes known as a group of endotrivial modules, and in that form the study goes back to the 70s, and what I'll focus on today is sort of a viewpoint using homotopy theory, but where in the end of the day it will be reduced to sort of various invariants in really local group theory. So the overall strategy is to start with this question in representation theory, then use some homotopy theory, and then get back to something which is computable in terms of local group theory. So that's sort of the aim. You can of course do this in many levels of generality. So throughout this talk, G will be a finite group. Historically, the study started with G being a P group, and I'll also tell the story there. So that was completely solved by Carlson and Tavenard in mid 2000s, and then I'll move on to a general finite group, and G will be a field of characteristic P, and P will divide the group order, otherwise things are trivial. And later, if I have time within the 50 minutes, I will also say something about what happens over an arbitrary Dedekind domain, which will be joint work with Achim Krause. Okay, so here we go. So we start with as I said, a finite group and a field of characteristic P, and then if we have a symmetric monoidal category with some symmetric monoidal structure, which I'll write as a tensor product, we can look at the Picard group, which is by definition the invertible elements under tensor product. So that's a general categorical construction which one can study. So for instance, as a warm-up case, we could consider the category of KG modules, so finitely generated KG modules. So that's a fine symmetric monoidal category with tensor product over K. And if we wanted to calculate the Picard group of that, we would get just the one-dimensional modules, because we have a notion of dimension of these things, and that dimension is multiplicative. So of course, if we have to get the unit out in the end, then both of these dimensions have to be one. So the Picard group in that case will be exactly the one-dimensional modules. And here we already see that in the case where we were dealing with a P group and the field was a field of characteristic P, for instance, then this Picard group would be of the ordinary module category would be trivial. So, but we want to spice things up a little bit by saying let's, okay. So what's good about this? What's hot about it maybe is that it's easy to calculate. It's just calculating one-dimensional representation. So we could also formulate it as H1 of G with K star coefficients. What's maybe not so good about it is that it's not a local invariant. So usually or sometimes in finite group theory, we like to study questions which are determined by the local subgroups. So you could ask abstractly, can you recover some quantity or some representation or whatever from the local subgroups, meaning normalizers of non-trivial subgroups. So of course, we don't allow the trivial subgroups because the normalizer would be the whole thing. Yeah, so P is not the trivial subgroup. Yeah. Okay, so so that's so we're sort of done with that, calculating the Picard group of the ordinary module category. So now we want to look at the Picard group of the stable module category. So what is the stable module category? The stable module category is where we take the module category and then we basically mod out by projectives. So we identify two morphisms if they factor through a projective module, if the difference factors through a projective module. So that's the stable module category, which we'll be considering. So that gives an equivalence relation on modules, saying the two modules agree or are equivalent if they agree up to adding projective modules. And later on, what we'll do is, so this is a category a priori. If you define it the way I said, it would be a triangulated category. And since this seminar series is called New Directions in Triangulated Categories or something like that, it's appropriate. But this actually also has more structure in the sense that it has a higher structure, in the sense that it's a stable infinity category, and I might get to that a little bit later, in which way it's a stable infinity category, and that will in fact be quite crucial to proving the results, knowing that it has this higher order structure, and then the triangulated structure will then be the homotopy category of that infinity category structure. Okay. In classical language, we are studying, as I said, the Picard group, but it's also called the endotrivial modules. So concretely, we're studying, so if you're considering the Picard group here, it's just the modules, the finitely generated Kg modules, which have the property that if you look at the endomorphisms over K, then that splits as a trivial module plus a projective module. So these are sort of objects that you might write up in an undergraduate algebra class. So that's of course nice. And I'll call that, I'll call this TK of G, or sometimes I'll drop the K and just write T of G. An old result by Pooch says that this is a finitely generated abelian group. So of course we know also from an undergraduate algebra class that finitely generated abelian groups are classified. So if we get in such a situation here, we ask ourselves, well, what is this group? That's a very naive question. And you can again ask the question which we asked earlier, for instance, is it locally determined? This wasn't the case for the module category, but maybe it might be for the stable module category. And the answer will in fact be yes, it is locally determined. Okay, so again, the examples were the one-dimensional modules from before. But we also already here now see that we have something slightly funny. We don't only have the one-dimensional modules. If the group has the property that it has a so-called strongly p-embedded subgroup, so that means that if we take the so it's written here, if we take the group generated by normalizers of non-trivial p subgroups inside a CELO subgroup, then this might be a proper subgroup of G. And this is a classical question in finite group theory when a group has a strongly p-embedded subgroup, and there's a classification of those, for instance, for p equals to 2, which does not use the classification of finite simple groups, and there's also a list of groups with a strongly p-embedded subgroup for p odd, but that uses the classification so far. So this issue when the subgroup is a proper subgroup of G is like a very, very interesting chapter of finite group theory. If there is such a proper subgroup, then we can construct these endotrivial modules in a classical way that we simply take a one-dimensional module and then we do reduce it up to G. So that might have some projective sum answers, but if we throw those away, then we get an endotrivial module, which might be a non-trivial module. So that shows that somehow this process of throwing away the projective modules has actually introduced some new interesting complexity to the problem. The other way we can construct endotrivial modules is that if we take if, for instance, we had a one-dimensional module, then we could take the projective a projective cover of that, and then we could look at the kernel of that map. So that's so this stable module category has a triangulated structure, and this would be the Heller shift, the loop functor. One checks easily that this is again a new endotrivial module. So this shows again that if our intuition was from the module category that we should just have the one-dimensional, then we have more here. So let me give. So I know some people like, when you give some examples, then it's sometimes nice to give examples of the examples, because sometimes the examples might themselves be in need of examples. So for instance, like very concretely, if we take the prime being 3, then we could look at the sign representation. That's obviously a one-dimensional representation. If we, we could also consider the symmetric group on 3 letters lying inside A5. That would be one of these strongly 3 embedded subgroups. And in that case, we could, look at the sign representation on the symmetric group on 3 letters and induce it up. And that would give us a non-trivial element in the stable module, in the group of endotrivial modules for A5, which did not come from a one-dimensional character. So these things definitely do occur. We can also look, this element which we call the loops of K. So we can ask what sort of element is that? That's in general a non-trivial element. So for instance, if we look at that in when we take the group equal to cyclic group of order 3, doing this would give us an element of order 2, simply because if we look at the resolution of the trivial module over the cyclic group of order 3, then that has period 2. So that says that in this case we have an element of order 2. We could also do the same thing where we did it over the symmetric group on 3 letters. But if we look, so again the field is F3. So in that case, if we just took the the twofold shift, then we would not get back to the trivial module. What we would get back to the sign representation. So in that case, the periodic resolution of the trivial module would have length 4, corresponding to the group cohomology is 4 periodic. So therefore that element has order 4 in that case. But if we for instance had done the same thing for a group of rank 2, then we would be in a situation where this class had infinite order. So these modules, like non-one-dimensional characters, exist, and you can give easily examples of them. A slightly less trivial question is, are there other modules which are not constructed from this process, where you just take, you induce this one like these, you induce from these strong one-dimensional characters, from these strongly p-embedded subgroups, you take shifts, things like that. And it turns out there are examples of such modules, and that was known, I guess, I don't know, like I guess Carlson telling us, you guys found those in the 2000s, like observed that they were the case, and this story will sort of give some topological picture of what that happens and things like that. Okay, so let me repeat what happens here if G is a abelian P group. So first, are there any questions? Can people ask questions during the talk, even though it's recorded?
Yeah, I mean, if you have any questions, you can ask now if you want.
Okay, I'll go on. So in the abelian case, this is was already settled by Dade, where he proved that if you have an abelian P group, then in fact this group of endotrivial modules is just generated by shift of the trivial module. So the abelian case is under control. We know there's just one generator, and this generator has finite order if the group is cyclic, and if it's non-cyclic, then it has infinite order. Okay. So then the question was, what happens for arbitrary p groups? And this was the Big Theorem by Carlson and Timmermans from 2005, which completely describes what happens in that case. So again, P is a finite P group. And let me just, for simplicity of stating the theorem, let me rule out the case where it's either cyclic, it's generalized quaternion, or semi-dihedral. So let me assume that P is not of that form. We know what happens in those cases. And in those cases, there's actually torsion, torsion elements in this Picard group, this group of endotrivial modules. So their statement is formulated a little bit differently to agree with what I'll say later, is that, you know, now we have a finite P group. So we can, of course, restrict to the elementary abelian P subgroups inside there. So elementary abelians in particular. So we can restrict to the elementary abelian subgroup. So what is an elementary abelian subgroup? Is just an element of the form set modular P to the K, right? So they lie inside there, and we know by the result of Dade, we know that we get in that case we get a copy. If the elementary abelian subgroup is rank at least 2, then we get a copy of the integers that way. Now we can, of course, look at all those restrictions. We can look at all of those restrictions to elementary abelian subgroups. If we restrict to elementary abelian subgroups, then we know by Dade theorem that we get a shift of the trivial module. And then we can note what shift that is. Right, so that gives us an element which we can view in the element of this group of endotrivial modules. Okay, and there now, then so of course there are some obvious compatibility between these conditions, because if you have a subgroup of rank 2 and inside a subgroup of rank 3, then you will have an integer in both cases, and these integers will have to match up. So whereas there, you know, there might be many elementary abelian subgroups, there are in fact not so many possibilities for what this what you can get here. So the obvious compatibility conditions which you have to impose on these elements is that if you look, then it has to be stable under inclusions and conjugations. Like a fancy way of saying that is that you can restrict your sum. Instead of taking all elementary abelian subgroups, you can restrict yourself to taking just, you take the poset of elementary abelian subgroups, you take the geometric realization of that. So that means that you're considering these chains. You're only taking the ones which has rank at least 2. That has to do with that if you took the ones which has rank, which had rank 1, then these would give you torsion elements. So therefore you don't have to take those. So you only take those which has a rank at least 2. And then you take those up to conjugacy, and then you take the group of components of that poset, because, you know, of course, if you pass to a zigzag between the different ones where it has to be stable under, then you have to look at the, you know, the equivalence relation generated by those zigzags. So topologically, that means taking the group of components. Okay, so their theorem says that this is an isomorphism if you impose some obvious conditions on these things, which I, for simplicity, call the Carlson-Tevenaz conditions, and they again just have to do with periodicity in group cohomology, because it's basically the condition that we know, what's called like the Borel-Smith conditions when we're dealing with, for instance, with group actions on spheres or something like that. So it says that if you restrict to a group and it has a rank 1 subgroup inside there, for instance, which for instance what was Q8 or something, like the Barthel group would be Q8, then that has 4 periodic cohomology, and this has to be respected. So you get some conditions this way that they very easy to state, but I want to give it here, which are, and these are the only conditions on the values you can take here. So this is a very very pretty result, and of course super hard to prove. So for instance, proving that this map was injective to show that apart from these cases you do not have any torsion was a long annals paper, and then they have a later paper in Schoenes where they prove that you can actually realize all these modules. So show that that this is exactly the image. So in particular, you get that the rational rank is you have a formula for the rank of this group, for the rank of the torsion-free part, which was known earlier by work of Alprin. So this is a complete formula for what happens for P groups. You give me a P group, and you can like work out what this group is here. And what also happens by some group theory, if the P rank is large enough, then the rank will actually be 1. So then this poset will actually be connected. So this issue where you do have a non-trivial group here, like where this group is not just the integers generated by shift of the trivial module, is specific to low-dimensional cases. So that's that theorem. Any questions about this? So the deal, of course, for arbitrary finite groups is to try to generalize the statement in such a way that it holds for arbitrary finite groups. That would be nice. So this is the statement, which is joint work with Toby Barthel and Joshua Hunt, which somehow gives a formula of this flavor for arbitrary finite groups, which has various other formulations which depending on how you want to view it. Okay, so the thing to remember, which somehow does not require any fancy machinery, is that that for arbitrary groups we have an extra piece of data. Namely, if we restrict our module so we have our module, and then we restrict it to V, well, then we have that this, as we talked about, then this is a shift of the trivial module. But this is just as a V module. But now the normalizer V also acts on this thing here. And this we saw already in the sigma 3 case, right? We saw that, well, even if we had the symmetric group on 3 letters and we restricted it to the 3 silo subgroup. Okay, the fire alarm is going off here. Maybe someone, okay, good. You restrict it to this 3 silo subgroup, we would get something that was 2 periodic, just as a C3 subgroup. But if we look at it as a module over the symmetric group on 3 letters, then it's 4 periodic. This was the sign I said before in the periodic resolution. And that we somehow have to remember in our model. We have to remember that when this normalizer acts on this group here, which will just be isomorphic to K, this will give us a one-dimensional character. And the key to the general case is to remember these one-dimensional characters everywhere. So the theorem, again here stated where we exclude these groups where we have torsion in the CELO subgroup just to make the statement easier, says that we have an isomorphism where now instead of just taking what we had before, where we for each elementary abelian subgroup took this type function where we took the number of shifts of the trivial module we got when we restricted to an elementary abelian subgroup. We now also just remember the one-dimensional character we have on that module. So that's an extra piece of information. And then NV has to satisfy these Carlson-Tevenaz conditions, these P group homological conditions we had before, but this is just a condition on the CELO subgroup. So this is something, the conditions we just had before. So these are the old conditions that we had before. But now we have a new condition, which is this character here. And where does this lie in? Well, the value of these elements lie in this functor, and this functor has both a copy of the integers, and then it has all the one-dimensional representations we could have here. But of course, this is not quite right if n is equal to 1. Because if the rank was 1, then we would not have the integers here. Because if the rank of the module was 1, then we had just a one-dimensional the elementary. This would correspond to the case where the elementary abelian subgroup was rank 1. Then we would just then we would have a finite resolution. So there, the integer is not well defined because it's not an integer anymore. It's just something with some periodicity. But that we can. So what would happen if we sort of change this number up and down? Well, the element we're talking about here is sort of, the question is what happens on the resolution of a group when we restrict it to an elementary abelian subgroup of rank 1. Now, if the underlying group was of order 2, then if we're dealing with a group of order 2, then the periodicity is 1. Like if you have a cyclic group of order 2, then the periodicity of the resolution is 1. And this cannot be changed by any funny action, because there are no funny actions on a group of order 2, because F2 star is trivial. But at odd primes, there is actually a condition which we then have to say, well, if we shift the integer here up and down, then we also change the character corresponding to the resolution, and that has to be respected. But if that is respected, then these elements are compatible. So these are the obstructions for such pairs to be realized. Right. So these are sort of the obvious restriction condition which sort of has to be satisfied for this to be well defined. And the function just sends a module to the restriction, and then this one-dimensional character. So so this formula is maybe a little bit of a mouthful when you first see it, and you can say, how do I calculate with this formula? So we'll do some examples. Questions? Right. So the way. So let me first give another way of viewing this formula, which was in some sense how we were led to it. Was you can also view it in terms of sort of like an obstruction theory viewpoint. So in general, you can look at this group of endotrivial modules, and then you can restrict it to the P subgroups. So then you can look at the restriction to P subgroups and all factor through the restriction on the CELO subgroup. So the kernel will be the modules which restrict trivially on CELO subgroups. So I studied them in an earlier paper where we studied where I call them CELO trivial modules, and they have occurred in the literature under other names. And so I identified it with this H1 of the P orbit category. So the P orbit category is the category with objects G mod P, where P is a non-trivial P subgroup, and the morphisms are the G maps. So that is the kernel of this restriction map. And what I also did in the previous paper is identify this group with, which you sort of in fancy language can say is the zeros Breton equivariant cohomology of the subgroup complex. So this is again, so this is a poset of elementary abelian P subgroups, and with the coefficient system given by H1 of K star. So this again, this is a formula which says that if you look at the restriction of that map, then it is exactly the sort of one-dimensional characters on chains of P subgroups, on normalizers of chains of P subgroups, which fit together. So that is the kernel of that map. So that is sort of saying that these conditions I wrote up before, where I had this type function, is saying that in the case where you just took this n to be 0 everywhere, then the conditions would just be saying that for each normalizer of a chain of P subgroups, or alternatively a normalizer of a chain of elementary abelian subgroups, we have to pick a one-dimensional character. And these characters have to be compatible under the sort of the natural notion of compatibility. Then we have a restriction map here, and the restriction map maps here into the inverse limit over the P orbit category. So this is saying, saying that these things have to agree on P subgroups. In particular, what is written here is that this group here is a fusion invariant. So this is an invariant which only depends on the fusion system of the group two. In general, the orbit category depends a little bit more on the fusion system, but this depends on more than just the fusion system. Then what we show is that this is differential, which goes to H2 over the orbit category. And this can again be factorized through H1 equivariant Breton cohomology of the subgroup complex with values in these one-dimensional characters. So this gives an obstruction for if you have so what we would have here in the classical language would be a type function in the sense of Carlson Tevenars and Mazza, Carlson, Tevenas, and others probably. So then it says that in order for those to glue together to come from here, then we have to have this compatibility condition satisfied with these one-dimensional characters. So and what we see from this model is that when p is equal to 2, d is 0, but not in general. And this non-triviality for p equals 2 is exactly to do with this formula on the previous slide, that you know, this character nu I wrote up is always trivial in the case where p is equal to 2, just simply because you can have no non-trivial action on F2. Yeah. So this statement is equivalent to the previous statement, but this is sort of a more homologically formulated statement. And sort of here, small celebratory note that these invariants are very computable and described just in terms of local group theory. So these are described in terms of sort of classical local group theory. And so, for instance, if this complex here is simply connected, then, for instance, this fundamental group will just be the G modulo or P prime of G. So this will give us that you know, we can calculate just in terms of, we take the group and then we mod out by all P subgroups. So then we get a P prime group here. So if this is simply connected, then this is a priori not a local invariant, but under this assumption, it becomes a local invariant, right? So, and these two are isomorphic. So also how you prove uniqueness of finite simple groups or something like that. You prove that this some building is simply connected, and that allows you to describe the group in terms of generators and relations. Okay. So here, let me mention. So Jon is here. So we have this ongoing project with Jon Carlson, myself, Dan Nakano, and Nadia Mazza, where we calculate a G for any finite group of Lie type. And the hard part here is, of course, to calculate this torsion part in this case. There's also, yeah. So, and we find that there are sort of very few cases where there are exotic elements. And I'm not completely defining what I mean by exotic element, but I basically mean an element which is not generated by the procedures I described earlier with like these one-dimensional characters or things induced from strongly p-embedded subgroups and shift. Then the only exotic, okay, I should have written torsion here. Torsion elements in this group comes from SL4F2 at the prime 2, SP8F2, F4F2 to the prime 5, E7 here, both at the prime 2 and 3, and twisted F4 of F2. And this is, I should maybe make a disclaimer. So this is, we are still in the process of checking all the details. So which is, it's as some of you know, it's been a long process to get all these. So this uses all this phi-d theory of Malle and Bouet and so on. So it's together with this fundamental group business. Yeah. But this is what the list looks like. I mean, the thing is just that it's a very small list, and so which also means that each of these modules, which are non-trivial, is sort of maybe interesting in its own, because you can, you know, then you have a concrete module that you can sort of try to look at. It's a very small list, and these modules are related. So as I started out with, you know, modules, endotrivial modules. Examples of those are one-dimensional modules. And Tits has this famous theorem showing that finite groups of Lie type sometimes have non-trivial, you know, unexpected one-dimensional modules at the characteristic. And this is, and these are sort of, you know, coming about in the same manner. So they are modules which are, so they will be torsion where the torsion will be sort of at the characteristic. So in the group of endotrivial modules, these modules here will be 2 torsion, and there's one which is 3 torsion. And these come about because there are these strange teeth group in local subgroups, and then somehow the group is not big enough that they can go away. So they're sort of, so it's not, in hindsight, it's not so surprising that you get modules of this type, but they come about as sort of generalized Cheats exceptions. So these not quite one-dimensional modules, but close. And yeah, and then other funny things about this model is that that right, that now you can try to calculate, and for instance, what is an example where this differential is non-trivial? So one example is for instance for the PSL3 FP where this has index 3 in SL3 FP. And here we're at the prime P. So if this map had been, if this differential always had been 0, for instance, then you would have that these groups would just be isomorphic. They have the same fusion, but they're not. The one has index 3 in each other. So it's not a fusion invariant. And also another thing is that these torsion-free generators cannot be chosen in the principal block, which was another question which was open. So let me see. So I've talked for 40 minutes, right? That's
yeah.
Okay, yeah. So just to give an example, like so for SL3, no, for the symmetric group on P squared elements. So this is one of the cases where you actually, so as I said, like when the group become very large compared to the prime, then the torsion-free rank is always 1. But this is, for instance, one of the cases where you get, yeah, with this has rank 2, and then you can ask, okay, is it, for instance, the torsion-free rank, is it equal to these stable elements, or what is the differential? And using this model, for instance, you see again, so there would be, if you look at this component picture, there would be 2 components to the group of endotrivial modules. There would be this thing called the big component, which would be the one with the containing one which has large rank greater than 2. So this component which contains elementary abelians of rank P, and there's another one corresponding to this this elementary abelian, rank 2 elementary abelian, which is obtained by having it act lines inside the symmetric group via the regular representation, and this has its own. So these are these 2 components, and then you can ask how these 2 components interact, whether this one-dimensional character I mentioned gives trouble here, and what we find is that it does. So the Carlson-Tevenaz condition would say that the dimension, the difference between this shift, which we restrict to the rank 1s, would be the difference would be P. That's just this homological condition. But then there's a new condition which says that this difference here has to be divisible by P minus 1. And this is simply because, since the Weil group over here, so the normalizer of this group is rather big. It's GL2 F3. Then you cannot have this puts a restriction on which one-dimensional characters you can have, which extends the one thing coming from the central element, and this puts a restriction on just by this homological up and down shift on what the value is here and what the value is here, because they have to agree here, and here you only have one choice. So that puts a restriction on the 2. You cannot, because the Weil group here is big, you cannot freely choose the one-dimensional character here, because you could try to, you pick something here, then it's forced what it is down here, and then you go up here, and then you say, oh, there can only be one up here because it has to extend to GL2 F3. So the more fusion you have, the easier it will be to have these extra restrictions on what can happen here. Right. So this is what happens. So in general, the image of this thing will always be p-1 torsion. So if you multiply everything, so if you multiply in the, let me go back in the sequence here. You know, we saw here that it had index index 3, where in general, if you multiply, you know, the image will always I thought I meant, okay. Yeah, so if you multiply, sorry, let me just go back to this here. You can ask what the image is here, and the image here will always lie inside p-1 times. So you always have that T of G lies inside p-1 times this limit here. No, sorry, the other way. It always lies inside the limit here. And if you multiply p-1 on the limit 0 here, so then it's squeezed between the two. I'm writing this a little bit badly. p-1 times the limit here is inside the image of the TKG under this restriction map, and this again lies inside, of course, the limit by definition. So this map here, it's not always surjective, but up to a factor of p-1 it is. Okay, good. Right. So that so you can play around with this formula also for these and you can also calculate this for you know, for these kind of groups fairly easily. And the idea of the proof is to view this. So now we come to the new directions type thing, that we have to view the stable module category as an infinity category, and then there's a theory of Achille-Mathieu which decomposes the stable module category as an inverse limit as infinity categories of the stable module categories of the P subgroups. And this is a statement of infinity categories. You might say, okay, you know, does that help me? It's probably powerful, but it looks very abstract. But now, for instance, if we take the Picard space of these things, then the Picard space of an infinity category is a space. So when we take Picard space on both sides here, so then we get the statement here. So then we get, you know, so then we get the Picard space of the stable model of this stable model category is the Picard space of this inverse limit. But then for abstract nonsense, this inverse limit pops outside, and then suddenly we have an inverse limit of Picard spaces of these stable module categories of the pieces. But now it's an old school spectral sequence between spaces, and we can analyze that spectral sequence, just like, you know, we did in the old days. And then we analyze what the spectral sequence is and use these results for vanishing of higher limits, and we make everything in this fairly abstract looking formula explicit, and then you can at the end you arrive at a very small spectral sequence which has zeros almost everywhere, but has two non-trivial groups corresponding to the H1, the H2, and the H1. So you get sort of a formula for what it is. So you have so in the spectral sequence, if you have an element which is an element in this lim 0, then in order to realize it, you have a uniqueness obstruction, which is these CLO trivial modules from before, which was this kernel. But we also might have a D2, which gives you an existence obstruction. and this is why we get this exact sequence from the beginning, and then you can go further and like further analyze. So this group here then identifies with this Breton cohomology group that I talked about, and this H2 is not this Breton H1 I wrote up, but it has this Breton H1 as a subgroup, and if you explicitly write up what this differential is, you see that this differential lands in this subgroup. So you have this spectral sequence completely under control. So it's not, I mean, in some sense it's not so bad in the end, but it requires both sort of this abstract machinery, but also a fair amount of translation to see that the abstract machinery actually produces something group theoretic in the end. So this concludes my remarks about the proof here. I can see that I'm also close to the limit of my time. So this gives a plug and play formula sort of that you can. Of course, it doesn't mean that if you have a group, it's easy to calculate. I mean, we had a lot of trouble with the finite with these finite groups of Lie type, but this formula is also by this, as I said, like this algorithm. This is Carlson-Tevena's algorithm for calculating what these endotrivial models are, which, for instance, means that you can do it also for the sporadic group. So David Craven used my formula there and plugged into a computer and quickly solved the remaining sporadic groups. So this means that we now know what these groups are for at least for the finite simple groups, and we don't have a complete answer in general. In general, they don't often, you know, if you have a product, you can easily show that you can't get some of these endotrivial modules. So there's still a little bit of fuss around the edges, but we are sort of I mean, we know quite a lot about what happens for arbitrary finite groups and over a field. And then, well, then this is of course the question, well, you know, what happens for a Dedekind domain? Because why not? So let me just, I'm close to the end of the time, but let me just sort of give a teaser there. So this is something I've been working with on with Achim Krause. And first of all, you might say, well, you know, why do that at all? I mean, and you can say that there's sort of two reasons, or maybe more. I mean, first of all, like if you do, the stable module category is actually a recipient of invariance coming from geometric considerations where you have chain complexes and things like that. Then you can actually produce something which happens over the integers. So it's not so crazy to want to understand the endotrivial modules from sort of a geometric point of view, also over the integers or over other you know, number fields or whatever. And also this, sometimes it's nicer to pass to things over a field or a ring of characteristic 0, because then you have character 0 at your disposal, which is nice for calculation. So yeah, so we have some results there, which I'll just, I mean, you know, so you can, so there you can lift, so you can lift, so this was already basically known by Alprin. He only did it for the P group case, and it was observed by Lasur, Marle, and Schulz that you can also do the lifting in general for a finite group. And what Achim and I did, we sort of rediscovered some of this, but also observed that you can actually say what the kernel is. So you can actually say what happens with this group of endotrivial modules also over a complete DVR. So for instance, if getting integers. And then the big question is, of course, well, how do you glue these things together? How do you glue the endotrivial modules for the different primes together? Which was, I mean, when we started thinking about this, we were sort of like, you know, we didn't really know what to expect. But the good thing is now that you can use characters here, because we're over a field of characteristic. Because, you know, if we if we do things over a dedicant domain. And the point is there that you can define a character, but this character will not be everywhere defined. It will only be defined on the elements, the P singular elements, or the R singular elements. So the elements which are not units in R. Because but this is well defined there because projectives vanish. I mean, the character of projectives vanish on these R singular elements. So therefore, you also have a non-trivial, a well-defined character on these elements here. Yeah, and then we have a theorem that the stable module category is the idempotent completion of over R is the idempotent completion, or this map is an idempotent completion. So this category here might not be idempotent complete. So there might be, idempotents which don't split in this stable module category, but this process of passing between the stable module category of the dedicant domain and all the P completions is exactly this process of adding these idempotents. So what this means in practice is that well, it takes some work. Then you see that you can explicitly write down what it means for an endotrivial module in all of these completions to lift. So it has to, you have all these partial characters. All these partial characters have to agree on the overlap. So that gives us a class function if they agree on the overlap. And then there's another condition, a rationality condition, which would be a real condition in general, that this class function has to come from a rational representation. So it has to abstractly be a representation out there which realizes this. This might not. We actually don't know in the case of endotrivial modules whether this is a real condition, but somehow in general it is a real condition. So, but then you can. So then you know what. So then you can. So this also gives you a statement on pick, right? If you have a description of the whole stable module category. So for instance, you might wonder, symmetric group on 5 letters. What is the integral stable module? What is the integral endotrivial modules? So it turns out it's set direct sum set modulo 4, direct sum set modulo 4. So you can do fun calculations also over the integers, things like that. Okay, I should stop.
Thank you, Jesper. Can we all please unmute ourselves and give Jesper a round of applause? Right, so if you have any questions, please ask them now.
Can I ask a question, Jesper?
Sure.
Yeah, please.
Hi. I was wondering what the end of that 4-term exact sequence you had with the endotrivial modules mapping into the limit over the P subgroups, and then you had the H2.
Yeah.
Over the
Yeah.
Do you know if that's in some cases surjective, or what is the co-kernel or the last map? Or
I don't know a good way. I mean, as I said, for the prime 2, it is always trivial, right? And but this group, the obstruction group, need not be trivial, right? So it's easy to see that this map is far from subjective in general. Also, in many cases, right? You can have high rank groups where this H2 is non-zero. It's sort of like a sure multiplier thing, which keeps being there also for bigger groups. But in those cases, the map will be trivial. It's a good question. I mean, we thought a little bit about it, and the natural thing is that it should be sort of have some Picard groupish like flavor. but
Okay.
how to make that precise, we haven't figured that out. So,
Okay.
but that would be interesting to
Thanks.
to know. Yeah.
Okay. Any other questions?
Maybe one more question. These integral endotrivials, so they could be obtained as the integral Helder shifts, I guess. Do you know this integral kernel of the restriction to P subgroups will look like the kg that you calculated for FP coefficients? Is there an analogous calculation for integral and zero trivial endotrivials?
I mean, the point is that the module is, I mean, this inclusion is fully faithful. So that means that if you know the endotrivial at all primes, then you know the endotrivial. So this, you cannot have, so sort of when doing this integral question, I mean, you basically have a list of things and you want to know which of those can be realized, and that then becomes like an extra condition, right? So you know, for each prime you have these conditions which have to be satisfied, and then you want to see whether things glue together. And the obvious obstruction for this would be, well, you know, all these character values which now actually happen over the integers have to be integral, because otherwise it cannot come from an integral.
So basically, the isomorphism with the H1 of the orbit category with coefficients in ±1, would this be similar calculation then for the integral zero trivial endotrivials? Like, have you thought about this in more detail?
Yeah, I mean, you can, I mean, right, I mean, so this, so this, yeah, so it shows that the obstruction to realizing things has, I mean, you have to look at the p orbit category for all the different primes, and then
I see.
And then you have to have that the character values are compatible there. So whether that, well, so for instance, in some cases, you know, you could be in a situation where all of these character values, were just identically one, and you would still be able to have strange endotrivial modules coming from the fact that these were, I mean, rationally it would just be the trivial representation, but of course this is a whole business with endotrivials. They're sort of quite close to the trivial representation, but they're not quite the trivial representation. But I haven't, I mean, your question is whether you can reformulate this in a snazzy way in terms of the, like the orbit category on all p subgroups for where the prime is allowed to vary. Right, and I think our formula definitely allows some sort of formulation along those lines, but I haven't thought through exactly what that would, if that would sort of be more illuminating than the general formula. I mean, it is basically right. I mean, this character theoretic is sort of fairly easy to get your hands on, right? Because it's just as I said, like these character values will just be plus minus 1, and then in some cases even just plus 1. So
okay. Thanks. I mean, the integral case appears more in the group actions on spaces, so that's why I was.
No, that was why Achim and I got thinking about it. So yeah.
Thanks.
Yeah.
Thank you. Any other questions? I have a slightly silly question, Jesper, and I basically asked Achim this when he gave a talk on a sub-project, this thing that we're talking about today here in Bielefeld. So have you thought about applying these methods to the stable module categories of infinite groups that Peter and Nadia studied?
Yes, I mean, I talk quite a bit with Stefan Schwede about it at a certain point of time. So what should be the case is that you can sort of look at, like, so what Peter and Nadia also study is when you consider not sort of, you have an equivalence relation where you're sort of only considering endotrivial modules, but where you're considering sort of relative to the finite subgroups.
Finite subgroups, yeah.
Right, and what seemed to be the case was that there should be a decomposition similar to what Achim what Akil writes up, but where you consider, where you have a spectral sequence where again it's an orbit category over the the finite subgroup of the infinite group, and then you have the stable module categories of those finite subgroups, and then you should be able to look at that should give you a spectral sequence, just like in our case, and then you can study that spectral sequence. And I think we sort of convinced ourselves that the spectral sequence was should be there, and then you should get, so the case that Peter and Nadia study is basically the case of a amalgamated product. So that would be the rank 1 case. Yeah. So then there they write up some exact sequence, and that should sort of be like a degenerate. I mean, that should be sort of a special case of such a spectral sequence. But I mean, but neither Stefan Schwede nor I are sort of
okay.
Are like was we were sort of trying to work out, but there were some technicalities which were
okay,
which were difficult to. I mean, it's probably. I mean, you I think you wrote me an email at some point asking, and I did. Maybe I didn't answer you, but if I had answered,
but that was 2 years. That was 2 years ago, I think.
Right,
yeah. Yeah. Okay. And also, I wanted
there
to
should be a spectral sequence. I mean, along those lines, and that would be interesting to work out.
Also, I wanted to make a comment, but I'm guessing it's known to you. So your last idempotent completion result seemed familiar to me because I had seen it in a paper by Toby. So I checked that paper, and he says that it has been studied in detail in a work in progress by Jesper Grodal and Achim Krause. So yes, there's no confusion there.
No, so he also got interested in the stratification results of
Do we have any more questions for Jesper?
But the funny thing here is that we actually determine what the image is in terms in sort of character theoretic terms, right? Which is sort of funny, because that means that you can. I mean, that's sort of what you want to know, right? You want to know, I give you some data, is it an endotrivial module or not, right? So I mean, of course, also interesting to know the abstract statement that it isn't. I mean, this shows that the inclusion is fully faithful and things like that, but there's also
I think for stratification, just knowing it's a symmetric monadal equivalence is like almost good enough. But in your case, like you give the image and like characterize it very neatly. Right. Yeah. Any more questions for Jesper? Okay, if there are no more questions, let's thank Jesper again. Okay, thank you all for coming. Next week we have a talk by Sergey Buk, and the week after that we have Unknown Yakutieli. So the details are on the website, and I will send everyone the details on the invitations, like when the time is right. Okay, thank you all. I'll stop recording now.
Hi, Ellen. I didn't want to say hi.